Hello all, welcome to this tutorial in which we will be looking at map estimates. Now till now in all of our tutorials we have looked at MLE estimate and then again an MLE estimate when we are assuming the data is from mixture densities. So now we will take one specific example and see regarding the map estimate. And I assume that all of you remember the idea of conjugate prior. So, in which the forms should be identical, which makes sense actually. So, we'll be taking one example of this particular form in which we will be assuming the parameter is from a Gaussian distribution, and then we'll be looking at the prior which is from a Gaussian distribution, and then we'll be obtaining the conjugate prior in the similar form, okay, in the similar functional form. Okay, so now without any further delay, let's proceed. So we are looking at the map estimate. So now let's consider my data I have is x1, x2, so on till xn I equals xn. Okay, so this is clear that I is from to n. Okay, this is the data that I have. Now then I can write that theta given this d is by Bayes rule can obtain given t divided by this normalizing value z. See, normally we used to write this as proportional. Now we're skipping it. So I'm just, for the sake of completeness, this is the prior and this is the conjugate prior. What should be the form of this class conditional or this conditional in the case? Okay. So now we are now let's consider a case in which we are only estimating the mean. Now we are assuming that it is from a Gaussian distribution, only assuming the estimating the mean. Okay, and then we are assuming that the variance is known to us. We're taking a very straightforward and simple case. Now consider estimating the mean of Gaussian density with variance assumed known. Okay, this is our assumption. So now then for a given x, now how will be it look like? Now 2 pi now exp of sigma square x minus mu whole square. Okay, now I'm assuming that all these are x's belongs to R. Okay, so now what do we have? Now mu is the only parameter that we want to estimate. Now in the case of MLE, we know that mu MLE now will be 1 over n summation I is equal to 1 to n xi. Now this is how it will be in MLE. So we have already seen this derivation in length. Okay, so now P of mu given d is by Bayes rule, d given mu, P of mu by this normalizing C. Okay. Now for the conjugate pair, we want uh, this pair and then its conjugate pair should be of the same functional form. Okay. So now let's make the note of this for conjugate prior. We want P mu and then D to have the same functional form. And so this is for one data point. Now what will happen when you have the whole D with you? D given mu, it's like division given mu, it will be 1 over sigma square 2 pi to the n exp of minus 1 over 2 sigma square summation I is equal to 1 to n xi minus mu. This is how it turns out to be. Okay. So now it is evident that this is a function of mu. Okay. So as a function of mu, this has an exponential of a quadratic in mu. Okay. So now what do we want our p mu? Now this is a quadratic, exponential quadratic in mu. Now when I multiply this, now I should retain the same form, same functional form. Okay, we need p mu such that when this I multiply with this specific thing, we need to get the same functional form as that of p mu. Okay, now it makes very clear that I assume it to be Gaussian. This is also Gaussian. I can combine them. So overall, finally, I'll be getting them in the term of the same functional form. It is pretty much clear from the setup itself. Okay, so let's make a note of that. So we need P mu such that when multiplied by mu, we need to get the same form as of P mu. Okay. So now this, therefore, the conjugate prior here is a normal density. Okay. So now let's assume that P mu is normal distribution with mu 0 and sigma naught square. And these are the hyperparameters. Sorry for that. Now, as you had in the beta densities, sorry, in the class, you looked at a conjugate prior. Now you had this alpha and betas that are sorry, There are hyperparameters. Similarly, here also, now we shall have these values are hyperparameters. Where you not okay, some what is this? Okay, it's not getting erased. Okay. Square are hyperparameters. Okay, so now again, we already know that. So P mu given D is equal to P D given mu into P mu divided by Z. Now we can eliminate this Z and substituting for PD given mu and P mu. Now this will be is proportional to exp of minus 1 over 2 sigma square summation I is equal to 1 to n xi minus mu whole square minus 1 over 2 sigma naught square mu minus mu naught whole square. Okay. Now mu is the current value and mu naught is what you have assumed. Now this is the hyperparameter that you have assumed. Please be very clear with this. Okay. So then this I can write it as this is proportional or same. Okay, 1 over of A. I can consider this whole thing that is there. This I have taken this half minus half outside, and then I can think this whole term as A. So I should not use proportional here. I should write equal. Okay. Now this is proportional to this, and this is equal to this. Okay. Now this A is same as 1 over sigma square summation I is equal to 1 to n xi square plus mu square to 1 over naught square plus n into sigma square minus 2 mu into summation I is equal to 1 to n xi minus sigma square plus mu naught divided by sigma naught square plus okay. This is what we get. Okay. So now suppose let's call this as equation. Okay, A have already been used. Okay, let's call this as 1. Okay, this is equation 1. Suppose we, sorry, that change. Suppose we have P of mu given D, that is also a Gaussian distribution with some mean and then some variance, now is normal with mu n, and I can write the form of this, and then I can equate the exponential part and then obtain the values for the mu n and sigma n, correct? Okay, that is what I am trying to do now. So now because of which P of mu given D is proportional to exp of minus half mu minus mu n divided by sigma n square. Okay, so now this is same as exp minus half mu square divided by sigma n square plus mu n square divided by sigma n square minus 2 mu into mu n divided by n square. Now consider this as equation 2. Okay, so now let's take this as 2. When I mean 2, only the one in the braces. Now you have a mu square here and then you have a mu square here. Now, therefore 1 over this sigma n square should be same as this. And you have 2 mu here. So mu n divided by sigma n square should be this term. Okay, this can easily be evaluated. Okay, and then if you substitute them, finally you should get this. Okay, that you can take it as a what do you call a check whether things are summing up together. Okay, so now let's do that. Okay, now comparing 1 and 2. Now comparing 1 and 2. When I mean 2, only in the brackets, what is that? So we get sigma n square is 1 over sigma naught square plus n plus sigma square. Therefore, this will be sigma square. Oh, sorry. No, sorry. This is not. This is 1 over sigma n square. Okay, will be this. Therefore, which implies sigma n square is sigma square into sigma naught square divided by sigma square plus n into sigma naught square. Okay, this is how you obtain this. Okay, now similarly if we do it for mu n will be 1 over, so mu n divided by sigma n square I equals 1 to n xi plus mu naught divided by sigma naught square. Okay, so now if you push the sigma n square divided by square, and then you have I is equal to 1 to n xi plus sigma n square divided by square into mu naught. Now, does this look familiar? There is one term missing. Okay, that is 1 over n. Now, this is similar to our MLE estimate for the mu that we have. Now, this is just off by some values, off by some scale, not off by some values, off by some scale. So, this is linear combination of my MLE estimate and then my assumption. So my map estimate, which is there, this is mu n is this. Now I get a whole distribution, and then since it's a Gaussian distribution, the mean, mode, everything will be same. Therefore, I'll be using the mode, which is maximum a posteriori, so which is same as the mean, which we have computed. Now what happens is, now this actually means that the mu n that we have computed, the map estimate mu n is a convex combination of the MLE estimate and mu naught. MLE estimate for mu and mu naught. Okay. So now for large n, the mu n will be similar for mu MLE. Okay. So this is the known result. And then we looked at here also, which makes sense. Okay. As n becomes very large, now as n becomes very large, the Bayesian estimate is same as MLE, is same as MLE. And please note that since we are dealing with Gaussian, the mode is same as the mean. Okay. So now let's make some, just note a since the distribution is Gaussian, okay, so mode as well as mean is mu n, which is a linear combination of my MLE and then the assumption that we have. Okay. So, in this tutorial, I just wanted to bring out the point that how do we look at the map estimate and then obtain the conjugate pairs in the cases of Gaussian densities. I hope it was nice and interesting. Thank you all. We'll meet in the next tutorials. Thank you. Bye.